Okay, so Math 30 is really just a continuation of Math 20. Some of you may have taken Math 20, some of you may not have. It just depends on how you're coming into this class. But the very last section I know in my Math 20 classes that I cover is actually 5.1. It's a nice little preview for those who did 20 to kind of experience what we're going to start with 30. We use the exact same textbook in 20 and in 30. That's why we start in Chapter 5 instead of Chapter 1. Which is where we start in 20. So if you did not take 20, feel free to go back in the textbook and look at chapters 1, 2, 3, 4, because that gives you a good idea of the stuff that we've already covered and the information that you should already have available to you. Chapter 5 starts with exponents, and that's where we're going to start with for Math 30. And so an exponent is the little number that's written above a base. So this base can be can be a variable, like a letter, or it can be a number. And what the exponent is actually telling us is how many times we take the base times itself. So we are never taking the base times the exponent. I'm not saying x times 2 and getting 2x. What I'm actually doing is I'm taking x times x. It's a nice shorthand so that if I want to take x times itself 10 times, I don't have to write x times x times x times x over and over and over again. Because one thing that we like to do in mathematics is we like to have things nice and condensed as much as possible instead of having it long and drawn out, because it helps us simplify things. And so that's what exponents allow us to do. Some of your homework problems are simply going to be navigating between a longer version and then a condensed version using exponents. So the first example that we have up here, we have x, 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 y, y, y. That's the expanded version. That is not the way we would typically write this because it's long and messy, and if I needed to add or subtract anything to that, it becomes very difficult. And so what we would do is we'd say, okay, well, I have a base of x, and how many of those do I have? I have 1, 2, 3, and 4, so I would have x to the 4th power. That's how you would read that, x to the 4th. Then I look at my y's. That's a different base, so I have to consider it separately. I have 1, 2, 3 of those that are being multiplied together, and so I would have y to the 3rd. There's two different exponents that kind of have special names. If we have y to the 3rd, you might hear people say that's y cubed. That's a special one. There's also, if you have something to the 2nd power, like we did up here, just in our definition, x to the 2nd power, that's also known as x squared. Outside of those two, x squared or x to the 3rd, x cubed, none of the rest of them have special names. We always just say to the something power is how you would read that. And today, with our exponents, we're going to learn a couple of different rules so that we can learn how to manipulate our exponents together. Are there any questions about how we actually condense our exponents or what it means to have an exponent, though? Okay. If at any point you have questions, just yell at me. So the first actual rule that we're going to learn is the product rule. These are very important to learn. We're going to have product, quotient, power rule. I think that's it for today. I think there's 3 rules. So the product rule is where we have the bases are the same of 2 different things, but the exponents may be different. And we can combine them together if they're being multiplied. Product means multiplication. So here we have x to the nth power. This m can stand for any number, times x to the nth power. If we want to combine those into a single exponent, what we do is we add our exponents. The base has to be the same, though, in order for us to do this. I couldn't use the product rule up here because I have a base of x and a base of y. Those are different. So this only works if the base numbers or the base variables are the same. We're going to do a couple of examples. I'm going to get some more paper, though. And you can't see that. What's on my screen is different than what's on yours. So there, now you can see it. we have 3 to the second times 3. I always like to start with this one because if we look at it, the first term, 3 to the second power, has a power. It has an exponent. But if we look at the second term, it's just 3. So you can actually write that with an exponent. We don't typically, because again, we like to keep things simple, and so we don't typically write the exponent here if there's just one of them. But if you just have a whole number or you have a single variable, what happens is that's actually raised to the first power. So 3 to the second times 3 is the same thing as 3 to the second times 3 to the first. And if we're using our product rule, we can condense this further because we can add those exponents together, giving us 3 to the third power. Now, you want to pay attention in your homework to see whether or not they want you to write it with powers or if they want you to write it with, like actually compute out what 3 to the third is, which is 27. Almost always they want you to leave it with the powers. Again, this is one of the reasons why I strongly recommend you use the homework first and you play around in the homework. That way you know whether or not it wants you to write it as 3 to the third or if it wants you to write it as 27. It's very specific. Next to the answer box, there'll be blue or green words that will tell you exactly which format that you should put in. But that is all we would do on this one. So let's look at another one. 2 to the fourth times 2 squared. What would that become? If we leave it in exponential form. Two to the sixth power, that's exactly right. Because using our product rule, we are allowed to add those two exponents together because our bases are the same. 4 plus 2 is 6. And let's see what our third example is. We will have, this is my z. My z has a line through it. So we will have z to the fifth times z to the fourth. All the other examples that we did had numbers, so I wanted to make sure we had one with variables. The bases are the same. Both are z's, so we're allowed to use our product rule. We just add the exponents, and we will have z to the ninth. Are there any questions on how to apply the product rule? Okay. There's no questions. You'll see in my handwritten notes, I did go ahead and show the equivalencies for our numerical ones. If you're not sure what 3 to the third power is, you can take 3 times 3, which is 9, times 3 again is 27. Obviously, when you get 2 to the 6th, that gets kind of large, kind of quick. You are more than welcome to use a calculator if you need to actually type that in. On this specific calculator, which is not necessarily the one you have to use, but I like to show this one because it doesn't have a exponential function in the way that you might think of it. So if I'm doing 2 to the 6th, you type your base in first, and then this little triangle is known as the caret. That lets you put in an exponent. So that little caret's telling you that the next number you put in is going to be your exponent. So if I do 6, hit enter, then I get 64. So some of your calculators will have carets. Some of them will actually allow you to type in, like the multi-view is really nice. It lets you type in the exponent, and it looks just like a regular exponent. And if you have a different calculator, I can show you on those as well. For most of this class, I won't use a calculator for a lot of it because I don't want you to grow dependent on technology. And so I will show you a lot of times the longer way to do things because it's actually more beneficial to you in the long run. Okay, product rule allows us to multiply our exponents together, and the quotient rule allows us to do division. Now, in 5.1, just as like a heads up, we don't really deal with negative exponents, which can happen. 5.2 is actually all about negative exponents. So next week, we will talk about negative exponents. So I'm actually going to show you two completely different ways to deal with dividing exponents. One of them is where your top number or your top exponent is larger. And if your top exponent is larger than your bottom exponent, like m is greater than n, then I recommend using the quotient rule. When you divide, notice that what we do is we subtract our exponents. When we multiplied, we added our exponents. Multiplication and division are kind of opposites of each other, same way as addition and subtraction are opposites of each other. So if your top exponent is larger, this is the method that I would use. And that's the method we're going to use first on the next handful of examples. So 2 to the 7th over 2 squared. Now, we could convert these to numerical numbers and then do division old school way. But with our quotient rule, we actually can just do it using the quotient rule where it says, since the top is greater than the bottom, like in terms of our exponents, I can subtract my top exponent from my bottom exponent. The top exponent always comes first, which gives me 2 to the 5th. And if it wanted a complete numerical answer, not with exponents, you could type that into your calculator and you would get 32. So quotient rule is pretty nice. We don't have to deal with big numbers and doing division and things like that. Y to the 13th over y to the 4th. We can do it with our bases being variables. My top exponent is larger than my bottom, so again I'm going to apply my quotient rule. Take 13 minus 4, which gives me y to the 9th. In Pearson, when you click in your answer box at the bottom, which I can show at the end of class, but in the bottom, there will be lots of little options for you to type in fractions and you to type in exponents. And it will allow you then to type these exponents in the way that they want you to. Okay, what about this one? This one's a little bit different. I said use the quotient rule if the top exponent is greater than the bottom. But when we have x squared over x squared, the exponents are the same. It is 1. How do you know that?
I took this course last semester, but it's online.
Okay, that's a fair answer. So anything divided by itself is actually 1. So if you take 2 and divide it by 2, you have 1. This is x squared over x squared, which is 1. But our exponential, our quotient rule actually works here as well. There's just a special little rule that goes with it. When you take 2 minus 2, you get x to the 0th power, not 6, 0. Anything to the 0th power is always 1. It's one of those special exponential rules. So that's a nice little note to put in. Anything to the 0th power is 1. And we actually prove that later on with logarithms in college algebra. But anything to the 0th power is 1. So if you think about it using exponents, this always works. If you think about the fact that anything divided by itself is 1, you can also think of it that way. Either way, you're going to get the same result. So that's using the quotient rule. Quotient rule works every time, whether the exponent is larger on top or not. But the problem is right now you don't really have the terminology or the ability to think about negative exponents and what that means. We will when we get to 5.2. So I'm going to show you a different way that you can approach doing these problems when the top has a smaller exponent than the bottom. And I call this process dividing by simplification. And this works regardless as well. So this is two different methods that you can use. Something, if you've never had me before, I'm not a my way or the highway kind of professor. If you have a method that works solidly for you and it's mathematically sound, that's great. I will never stand over your shoulder and say, that's not the way I do it, you have to do it my way. Especially when we start going into factoring and things like that later on. I know there's tons of different methods, and some people like the box method or the butterfly method or the X method and all this other stuff. And it's like, if that works for you, great. So here's another method that you can use in order to divide these with exponentials. And I'm going to show you specifically when the top exponent is less than the bottom exponent. Because if I used my quotient rule on this, I would be taking 3 minus 6, which would give me a negative exponent. And at this point, I don't know how to deal with that. And if you type x to the negative third as your answer, you will get it wrong, because we don't like to leave negative exponents. So here's the way that I do it using simplification. And there's really two different versions of this, but I'm going to show you the long version first. X to the third means x times x times x, right? There's 3 x's being multiplied together. If there is x to the 6, notice that we have 6 x's being multiplied together. Anytime that we are doing division or we're needing to simplify a division problem, if there's the same thing on top as on bottom, you can cancel it out. You can simplify it away. So I have an x on top and an x on bottom. Those can cancel out. X on top, x on bottom, those can cancel out. X on top, x on bottom, those can cancel out. So what I'm left with now is I have no x's on top anymore, but I have 1, 2, 3 x's on bottom. So I have 1 over x to the third. Now some of you might be like, oh, I don't want to write out all these x's. What if I have x to the 200th power? Obviously you don't want to do that, and you will have better tools to help you with these problems after 5.2. This is a good tool to use until after you learn 5.2. Another way you can think about this is we had x to the third on top, and so I'm going to kind of think backwards a little bit. And can I split x to the 6th into 2 things, kind of going backwards with my product rule, so that I have an x to the third and an x to the something? Yeah, I'd have another third. Because if I use my product rule to combine these, I would get back up here. Because product rule, you add your exponents. So this would be x to the third times x to the third. Notice again, I have x to the third over x to the third. Those would go away, and I still get the exact same answer. This method, or this way of looking at it, allows you not to have to write out all the x's or all the numbers or whatever the case may be. And you still do the cancellation the same way. If you already know how to do negative exponents, you can use negative exponents. But this is the type of answer they want. They do not want your answer in terms of negative exponents. Let's do another one. I'm just going to slide it up. We have z to the second over z to the third. And I'm going to do this one even another way, because I like to present as many ways as possible, and you pick which one clicks. If I look at these, where do I have more z's? On top or on bottom? Bottom. I have 3 on bottom, 2 on top. So I have more on bottom. How many more z's are on bottom? 1. I have 1 additional z on bottom. Same thing works with the x's that we just did. If I look at my x to the third over x to the 6th, where do I have more x's? On bottom. How many more x's do I have? I have 3 of them. So just another way to think of it. Whichever way clicks, if you need to write out the z's and cross them out, if you need to break it apart and cross them out, if you want to look and say, where do I have more of something, and then go that way. If you know negative exponents and you want to go ahead and utilize them, you can do that. Are there any questions on these? Okay. Let's do a little bit of simplifying before we learn our power rule. Let's look at, this uses our zero exponent rule. We're going to look at that one versus this one. Versus this one. When it comes to algebra, and especially when it comes to exponents, parentheses make a world of difference. A world of difference. The parenthesis is going to tell you what all is included or raised to a specific power. If there aren't parentheses, then the only thing being raised to the power is whatever is right in front of it. So for A, I have 5x to the 0th power. This 0th power only affects the x. It has nothing to do with that 5. I can write this as 5 times x to the 0th power, because that's exactly what it says. It's just when we have a number next to a variable, we oftentimes don't write that multiplication symbol there. We like to keep it simple. But when I split it by putting a multiplication symbol in there, it makes it more obvious that this exponent only goes to that x. And so, as we said previously, anything to the 0th power is what? 1. So 5 times 1 is simply 5. What do you think B is? 1. It is 1. This 0th power goes to everything that is inside of here. You can kind of think of it as you are going to use your distributive property to distribute that power inside, to where you would have 5 to the 0th power times x to the 0th power, because that power applies to everything inside of there. Well, 5 to the 0th power is 1, and x to the 0th power is 1, so 1 times 1 is 1. Do you have to show all these steps? Absolutely not. But I like to make sure that the connections are being made, because you will be distributing powers that are not 0 and that don't just go away to 1. And so having that set of parentheses there really makes a difference. And so you have to be really careful with that. There's another problem I will show you that is very key to this as well after I do these. We'll do this last one. So here I have 5x y squared z to the 0th power. This one's very similar to the first one, but again, I wanted to accentuate the fact that that 0th power has nothing to do with the 5 or the x or the y. It only affects that z. So that z term ends up being 1 and everything else stays, so that you get 5xy squared. We can't combine anything else because all the bases are different. I like to point out the parenthesis thing because some people don't use parentheses, some do, but these obviously mean very different things. There's another problem that I bring up in pretty much every math class I teach, because it's so integral to understand that how powerful the parentheses are. And it's this one. I guess you can call it D and E, even though it's not in my scanned-in notes. This one usually makes students mad, so I'll apologize before we even do it. What do you think D is? That makes me happy. What do you think E is? 4. Yeah. D is -4. And luckily, most calculators now catch this, and they actually will produce out the right answer. I have had students, though, in class type these into their calculator the two different ways, and they will get the exact same answer. And these are not the same answer. And that really aggravates students a lot, because when we see this negative, we usually just lump it right in with the number that follows it. But what this is actually telling us is that we have a negative 1 times 2 squared. It works just like this previous problem that we did up here, where we can pull that number off the front and separate it, and then you can truly see that that second power only goes to that 2. It has nothing to do with that negative because there's no parentheses. And since it has nothing to do with that negative, the only thing I'm taking times itself is 2. 2 times 2 is 4, meaning I end up with negative 4. Over on E, though, this is all clumped together. So I'm also going to take the negative times itself, and negative times negative will produce a positive. And your calculator now, I tried it on at least all the calculators that I have, and they all caught it. But I have had students whose calculators did not catch the difference between this. And that's because calculators are programmed by humans, and it's programmed in such a way that they're there to try and catch the mistakes that you might put in. So just be careful with this. This is a huge concept that if you don't catch it now, it can really screw you up later when we get into quadratics or we get into more complicated equations and we're solving for different values and we have to plug in negative values. And if you plug in negative 2 squared and get out a positive 4 when you're supposed to get out a negative 4 and things like that, it will mess up your entire problem. And it's super frustrating when you fill half a piece of paper with work and it's wrong all because of a negative. So, questions on this? Okay. Then let's learn our last rule. I think it's the last rule for today, which is our power rule. Our power rule is when we have an exponent raised to an exponent. We have an exponent raised to an exponent. We can multiply those two exponents together to combine into one term. So power rule, we take the exponents and we multiply them together when we're raising a power to a power. So for A, I'm going to show you actually why that works, because it's relatively small. We have 2 to the third raised to the second power. So if I apply my power rule, that would be 2 to the 3 times 2, which is 2 to the 6th. When I have 2 to the third, what happens is I have x, or I'm going to use x's even though it said 2. So I have x, x, x. That's x to the third. If that's raised to the second power, what that means is I'm going to have a whole other group of those that are exactly the same, which gives me 6 of them, which is why the power rule actually works. Now, obviously, when we get really large numbers, like even with our third example, I don't know about you, I don't want to end up writing all those little z's out. So the power rule is really nice and it helps us to simplify things pretty quick. So what would be B? If we have x to the third raised to the 4th power. X to the 12th, because 3 times 4 is x to the 12th. And we do the exact same thing over here. There's no changes, just the numbers change. Z to the 6th raised to the 9th would be Z to the 6 times 9, which is Z to the 54th. Any questions at all before we make it a little bit more complicated? Okay. So what if we have more than one thing inside of our parentheses? I'm going to zoom out just a tiny bit. What if we have 2 terms in there, or 3, or 4, or so on and so forth? This is where we're going to think about distributing the power that's on the outside. Now, you don't necessarily have to write all those out if you don't want to. I just wanted to give some pretty broad examples so that you could see and be able to apply them later. This first one, we have x times y inside, raised to the nth power. This is really similar to the 5x inside the parentheses that we've raised to the 0th power. What we ended up doing is we took the 0th power to every term inside. We distributed it, which is what we're doing here. The same thing's true if we have a quotient, if we have an x over y raised to the something's power. We can distribute that power to each term, the top term and the bottom term. And then we can have a combination of both, where we have actually 2 terms on top and 2 terms on bottom. All of that's being raised to some exponent. We can distribute that exponent inside to everything. So that's not really a new rule. That's why it doesn't have a new name or anything. It's just applying the power rule to our products and our quotients. So here we have negative 2/3 times x to the 6th times y. We have 3 different terms at play, but all of that is set inside of our big parenthesis being raised to the 3rd power. So that 3rd power is going to apply to every single one of these. So I'm going to write it out the long way so that you can see what's happening, where I split up each of these terms. My first term is my constant term, my number, where I have negative 2 to the 3rd. And that is raised to the 3rd power. My next term is my x to the 6th term, which is being raised to the 3rd power. My next term is my y term, which is being raised to the 3rd power. So I'm just really showing you how we are using the distributive property to bring that exponent in to every single one of our terms. Negative 2 to the 3rd power over 3 to the 3rd power. You can keep writing it out the long way if you like. Whoops. That's a 3. Using my power rule here, I have x to the 6th to the 3rd. So that'd be x to the 6th times 3. And then here, there's no exponent on that y, so we understand that to be a 1. So that'd be y to the 1 times 3. Again, you do not have to go through necessarily every single one of these steps. When we are first learning a concept, a lot of times I will do all of the baby steps in the middle, and then as we get more comfortable with it, we will move quicker through them and we won't write out all those steps. Negative 2 to the 3rd power is negative 8. 3 to the 3rd power is 27. Then we had x to the 18th, y to the 3rd. Obviously, this one's a little bit more complicated than just x to the 6th to the 3rd. When we start adding numbers and exponents and things like that, it gets a little bit more time consuming. Are there questions on this one? All right. We have p to the second over q to the third raised to the fourth. So again, the process that I'm going to use is I'm going to bring this power into every term that's inside. That would be p to the second raised to the fourth over q to the third raised to the fourth. Using my product rules, I would multiply them together, or my power rules, excuse me, I would multiply them together, giving me p to the 8th over q to the 12th. I can't simplify it any farther because the bases are different, so I can't do any type of canceling out. They're not the same thing. Okay, this one's exactly the same as the last one. We're going to bring that 3 in, the power of 3, and it applies to the 2. It applies to the r squared, the s, and the t to the 4th. That'd give me 2 to the 3rd times r squared to the 3rd times s to the 3rd all over t to the 4th to the 3rd. 2 times 2 is 4, times 2 is 8, r to the 6th, s to the 3rd, all over t to the 12th. X to the 3rd, y squared, all over 3x y squared. All of that's raised to the 3rd. This one is different than the other ones we've done so far. A, B, C are all different than this one. And the reason that this one is different is if we look at it, this is the first one out of these more complicated problems that we've had where we have a number both on top and on bottom. We have an x term on top and on bottom. We have a y term on top and on bottom. We have stuff that's the same on both the top part of our fraction and the bottom part of our fraction. Now, we could approach this problem the exact same way we approached the problem right above it. We could distribute that third power in there, and then we could just finish it out. I highly recommend you don't do it that way. And the reason why is because when you take 9 times 9, which is 81, times 9 again, you start getting really large numbers. And then if you're looking at the end and thinking, is this simplified? Because you always want to submit a simplified answer. The larger the number, the more complicated it is, the more likely you're not going to see if stuff cancels out. So anytime that there are similar things on top and on bottom, you always want to simplify first. You won't necessarily get a wrong answer if you distribute that exponent and do it exactly the same way we have been, but there is a higher likelihood that you won't realize it's not simplified at the end. So I always recommend simplifying first. If you simplify first, you will have much more manageable numbers and manageable exponents, and it makes your life so much easier. Because 81 times 9 is 729. And I don't know about you, but looking at that, I wouldn't know off the top of my head if 729 over 27 simplifies. Like, I would look at that and be like, that's a gross number, and I'd probably leave it. But if I simplify first, then I'm more likely to be able to catch the simplifications up front. So here's what I'm going to do. I'm going to look and I say, okay, I have a 9 over 3. Do those have anything in common? 3. 9 is 3 times 3, right? So I'm going to write it like this. And then the rest of it, I'm just going to write the way that it is because I think we are capable of doing it a simpler way. But I like to do my numbers and split them because then it's really obvious that they both have a 3. And remember, we talked about a number divided by itself, or anything divided by itself, is 1. So 3 divided by 3 is 1. It goes away. So we can cancel that out, leaving us with only a 3 inside. And it's on top. And then I look at my x's. Where do I have more x's, on top or on bottom? On top. How many more x's do I have? 2. And then I look at my y's. I have y squared over y squared. What happens there? That's right. Those things cancel out the same way my 3's do because I have the same thing on top as I do on bottom. So now I am applying this outside third power simply to 3x squared instead of all this other stuff, which makes it so much easier. I would much rather deal with 3 to the third and x squared to the third than all that other crap. So simplifying first really does make your life better in a lot of ways. In my handwritten notes, there are 2 additional problems. Actually, there's a couple additional problems. There is this one, which again works pretty much just like this one that we just did, where I'm going to see if I can cancel anything first, and if I can't, then I just apply my power. F, I look inside my parenthesis, there's nothing to simplify. I look inside this parenthesis, there's nothing to simplify. So I'm going to apply the power, and then I'm going to multiply the things together. I added G and H a few years ago because I thought they were helpful to see. We had x to the y over x. There's no powers to be distributed or anything like that, but I can simplify by simply canceling out my x's, which leaves me with just a y term. This one, I don't know why I put it cannot be simplified. Theoretically, it can be simplified a little bit, but not in the way that you think. So I'm going to write next to it. A lot of times, what people will do with this problem in particular, I see it in almost all my classes, is they say, okay, we have an x squared plus b squared over a, or excuse me, a squared plus b squared over a squared. And you're like, oh, they have an a squared and an a squared. And you guys will go like this and say, okay, my answer is b squared. I see it all the way through college algebra. I see this all the time. That's what I call magic math. It's not right. You cannot do this. We can split this problem. So this is magic math. Magic math is wrong. But we can split this problem to where we'd have a squared plus b squared. All of that's over a squared. That's the original problem. Notice there's only one thing on bottom, the a squared. I'm so sorry, that's really tilted. Neat. There's only one term on bottom. So we can actually split this. So we would have a squared over a squared. Because when you combine fractions with common denominators, you just add the tops or the bottoms and you leave the numerators alone, or the denominators alone. So when I do this, you'll notice that this first term is a squared over a squared, which is 1. But I can't do anything with this second one. So you can simplify it a little bit, but not in the way that you would be most tempted to do so, where you just cancel the a squareds and it leaves you with a b squared. So be cognizant of that one. Be aware of that one. That one's a little bit different. And I like to show that one early on because that one will come in later when we talk about rational equations and things.